today's webinar is the second webinar of our webinar series on open access and open science. And there will be more webinars each Wednesday in October. And this will then culminate in a panel discussion on the 29th of October, which will also mark the end of Open Access Week at the very end of October. In today's webinar, we will focus on why you should build open source software and how you can do it successfully. And this is where I would like you to introduce you to our two speakers. Next slide, please. So I'm really happy to have both of them here today. I would first like to introduce you to Brice. Brice is currently a PhD student at EMBL-EBI. He studies computational microbial genomics, and he's very enthusiastic about contributing to the bioinformatics community. He also has developed an open source tool and will tell a bit more about this in his presentation. And he will also talk about his motivations to contribute and build open source software. The second speaker is Renato Alves from EMBL. He is the bio-IT project coordinator there, and in his role, he provides computational support for the research community at EMBL. He has a very long experience in contributing to open source software projects, and today he will talk about how you can build of methods and approaches that help you to build open source software successfully. As I said, I'm very happy that both of them are here. Thanks for you for speaking today. And with this, I will hand over to Brice.
Yes, okay. So hello, everyone. So yeah, as Alex said, there's in the title, you might have seen like two sort of parts to the talk. One is why build open source software, and the second is how to do it successfully. And I'll cover the part one, so the why. And before going into it, we have to sort of define open source software, which you might hear me abbreviate as OSS. So I've identified two key sides to a definition. The first is that it's a piece of software that needs to be distributed with the source code. So it's not just an executable, a binary, but you need to have access to the programming instructions, so the code. More often than not, it will be publicly available, though it's not strictly part of the definition. And typically you can find it on the web, like on GitHub. But the second part of the definition is that the code needs to come with a license that allows the free reuse of the code, free modification of the code, and also you can sell the project. And the key provision here is that you need to maintain this license in the code that you use. So there's a sort of more comprehensive definition on this website, on the Open Source Initiative, and they also give you a list of the different licenses that that would qualify your software as OSS. So I can point you to there if you want more. But essentially today we're just going to focus on a piece of software that's easy to access, that's open, that you can probably get from the web, and that you can freely modify and reuse. So that's the operational definition. Let's just look at a couple of reasons not to build OSS. I think they're pretty obvious, but it's good to just mention them. One of them is if your software is for profit. So typically, if you develop it in a private company. We're not going to cover that today because we're coming at it from the research side. But another reason that I think can happen often in research is maybe your software will lead to a publication or your method. And in that case, if you're in a maybe competitive field, it might be advantageous not to release it at the very early stages. So here there's a bit of a distinction between developing from scratch in the open and releasing your OSS at a given milestone, typically a publication, for example. I'll touch on that a tiny bit more. But yeah, now I'm going to cover a few benefits of OSS development for scientific research. And I just want to make a tiny distinction here between writing sort of scripts that may process your data or produce plots for supporting a publication, and sort of developing a tool or a method for not just your specific data set or your research question, but maybe more broad data sets. And in that sense, developing a sort of fully fledged method or tool in an open way. And we're going to focus more on the second part, but we're happy to discuss both at the end as well. So I've identified three sort of main reasons to motivate OSS, and I'll give you some personal examples along the way. So the first has to do with the theme of the webinar series itself. It's open science. So I think we all agree that scientific research should be reproducible. And, you know, along the same lines, any computational research should have source code that supports reproducibility, that should be accessible, testable, reusable. In some cases, depending on, for example, what research or where you want to publish, being open source is a requirement anyway these days. So, for example, I've taken Genome Biology here, which is a good bioinformatics journal. And they have a provision where if you want to publish a method or software, you have to deposit the source code in a public repo with an OSI compliant license. OSI being this open source initiative that I introduced at the beginning. So another theme of just science in general is enabling progress. So I think we also agree that research should be sort of made public and publicly available for the scientific community as a whole to use. And again, this should also apply to research software. And I think there's now like a sort of large number of projects that are very successful and are open source and enable a lot of research on top of them. And I've just taken one example here. It's the Python machine learning framework scikit-learn. And last week when I checked out the GitHub repo, I saw that there were 263,000 other repos that use it. So it's sort of, it's enabling a massive amount of research, and that could be a pretty gratifying reason to develop these kinds of tools in the first place. Just along the lines of this sort of standing on the shoulder of giants thing, I'm a PhD student, and I develop a core part of my PhD is developing a tool, and it is open source. And I've just listed a few of the dependencies I have. So the other open source tools that I use, some of them are for building the project, others for testing, and others for just doing sort of genomics work. And along those lines, I mean, I couldn't really have developed this tool without all of these other ones. So it's a nice sort of, there's a nice framework of growing a network of tools that can help each other. Okay, so that was for open science, and now I'll touch on scientific credit. So software is increasingly recognized as its own scientific output, not just a research publication. Software is actually can actually be published as well now. So there are purpose-built like repositories where you can archive your OSS. And then they'll also give you a sort of citable DOI, so like a digital object identifier. For example, there's Renato that will do this for free, so they can take your GitHub repo and give you a sort of citation and a stable archive of it. So then you can tell people if you use my tool, please cite as. And the step further from that is journals that are purpose-built around publishing peer-reviewed OSS. So I've taken the Journal of Open Source Software as an example here. They published almost for free, but there is peer review, and you can actually also even sign up to be a reviewer. So, I mean, I'd recommend that if you're into OSS. My personal story here is I've been contributing to the Python bioinformatic workflow manager called SnakeMake. And 2 years ago, there was a request for formatter, because SnakeMake has its own sort of mini language on top of Python, and people like to format, code in general. So there was a request for this, a formatter for SnakeMake files, and I'm together with another PhD student at EBI, we decided to tackle this. So we built this tool called SnakeFormat a few months later. Sort of the prototype, and then we released the first version a few months after that, and we've got sort of the 19 releases in total since. But the nice thing is, and this is along the lines of scientific credit, is that we then made it to the the new SnakeMate paper at the beginning of this year. And you can see I'm here, and that's Michael, the other PhD student. So, you know, I would even argue as a young like scientist, if you and if you like programming as well, it can also be a pretty good career strategy, actually, on top of building useful tools, hopefully. Yeah, so those are the two motivations: open science, scientific credit. And let me just move to the last one, which is around building communities. So if you write this sort of open source code out there in the open, you can tap into a pretty massive community of both users and programmers. And the things they can give you are, there are many of them. Some of them, they may just suggest things or ask for new features. Some of them may try your program and then file bugs or issues. Some of them, if they're really keen and kind or a bit of both, they can actually propose fixes for your bugs and issues, and you can take them in via pull requests. That's on GitHub, for example. And then generally speaking, there's also it's nice when you have open source software to have open discussions, and you can sort of go through them. On GitHub, for example, it's pretty well done. So just quick example. The thing that's important here is like people will give up a lot of free time and energy, maybe their evenings and weekends even to develop OSS. And so, tapping into this community can be incredible, provided maybe the part 2 of our talk holds, which is how to do it successfully. So we'll touch on that. So my quick examples are for this SnakeMate tool. There's a total of 8 other people so far who have contributed, and these are some of these I've sort of never met before, and it's nice because it helps advance the project, but also feel like you're part of the community. For discussions, I just want to give a quick example for my PhD tool. So there was an issue, ages ago that we raised, and then the person that develops the sort of lead competing tool from us pointed at some solutions, which was very kind. And later on, this other sort of bioinformatics person who developed tools sort of pointed to this discussion, saying, yeah, there's some nice discussion for solving our own issues here. And I think, generally speaking, I was saying at the beginning, maybe you don't want to do OSS because it might open you up to competition. But I think there's potential for this positive competition and people actually helping each other out, despite maybe doing the very similar things. The other side of building communities is ensuring sustainability of your tools. This is also known as a pretty tough question in academic labs. Like, what does a tool become after the PhD student who works on it leaves, or the tool or the research is published? That's maybe you just move on to the next tool or the next bit of research, but who's going to take over the maintaining that tool if it's useful for the community? So I think 3 main answers. One is free developers in your community. So if you've managed to build that, and if you've managed to tap into people who are passionate, that can be good. It's obviously not something you can necessarily depend on. Another solution is institute level support and maintenance. One example at the EBI that I like, because I've used it before, is part of Ensemble, which sort of annotates vertebrate genomes. And they have this VEP, so it predicts the functional effect of mutations. And this has sort of dedicated support and funding from EBI for maintenance, and it is OSS. And a third avenue, which I think is exciting, is dedicated funding from various sources. The one I want to cite is the Chan Zuckerberg Initiative for Essential OSS in Biomedical Science. So they've done 4 rounds of this so far, and the latest one, they've given between $100,000 and $400,000 over 2 years to quite a lot of projects. And I encourage you to check out what they funded, because they're good projects in general, but also their list of criteria for how they select who receives funding, because that can give a good sort of idea of what's valued for actually funding these projects. And essentially, we're going to cover a lot of them in the second part. So with that, I will hand over to Renato for how to do it successfully. Over to you, Renato.
So as Brice mentioned, I will now try to give a little bit of an overview of if we want to tackle this challenge, how can we do it successfully? So the first step, and before we actually dive in, I just want to say that a lot of what I will be presenting is based on work that has been done over the past 2 years or so as part of a work group in Elixir, where we tried to define a software management plan that will be made available next week, most likely, as a preprint on bioRxiv. And among other things, it defines a set of steps and a set of assessment points that you can do to your software to understand perhaps what you may need to do next if you want to improve your likelihood of reaching this success with your project. So to begin with, I would like to define 5 stages of your project. So the first stage that we call inception is where you're still conceptualizing your project. Perhaps you have some ideas that you want to explore, and you already started planning a little bit things, thinking about some of the aspects of what you want to tackle, what is the problem, and so on. You may have then a second stage where you already have a prototype or a proof of concept, and this is something that is already workable, but is not yet released. So the release would come in the application stage, where you might have a beta version or an alpha version. There's the first label on your software. So for instance, as Brice mentioned before, there was this 0.01 version of the snake format tool, and there's also some initial quality assessment of your tool. Then in a later stage, you have production. So this means that you already have a stable software. You perhaps already have it even working in real world situations, in HPC clusters or something of that sort, and you're already considering how to make it more scalable, how to make it more accessible, more available to other people and in different systems, for instance. And then the latest stage would be the publication, where perhaps considering if the software was the primary goal of your research, you would be publishing the software itself, or if instead the software is not the primary goal, but you will be publishing results that you produced with the software. So throughout the presentation, I'll be using these color codes on the right side of my slides to highlight for every stage or for every aspect that we are discussing, what would be the preferable stage of where you would consider implementing this in your project. So to begin with, license. So as Brice mentioned, there are many different kinds of license that we can choose from. The main point here is that we want to choose something that enables people to collaborate with us, and this goes both ways. So here I would highlight the choosealicense.com website is one of many. There's many websites out there that can give you an overview of aspects of different licenses. What are the benefits of them? What are the downsides? Personally, the ones that I tend to use most are of the more permissive and simpler type, like the MIT license or BSD licenses. But you also have the more copyleft oriented new GPL licenses, which although very open source, they do have this aspect of caring about sharing improvements, which is as much as a positive thing, but can also be a negative thing. So if you were, for instance, a commercial company, this may be a deterrent because whatever improvements you do, by using software with these licenses, you may be forced to actually give back these improvements to the original authors. And so this may be restrictive. So this is among the aspects that you may need to consider at this stage. Now, following from this, we do want to do things in the open. So the first thing is if we want people to collaborate with us and we want to have a platform for everyone to kind of communicate on. So the first step would be to define a contributor guide or contributing guide. And this is something, this is a document that answers questions such as, so how should contributions be made? If, for instance, we are using a code versioning system as we should, then exactly how what kind of procedure do we follow? If we are using some kind of GitHub or GitLab platform or an issue tracker and so on, how do we centralize the discussion? How do we manage the different resources, the different requests that come in, both for new features or modifications, including bug reports, as Reese already mentioned, but also some additional points about clarifications or discussions. And this could be something within the platform that you're using, or it can also be built on top of existing platforms, such as, for instance, Matrix or the Libera Chat, which is a slightly older IRC technology, where a lot of open source people and enthusiasts come together, and there's channels on different topics. So you may find channels there for R, for Python, and pretty much most of your favorite tools that you will find in the open source world. And then on top of this, you may also want to consider aspects of code style, and how to credit whatever contributions your authors or your contributors will give to your project. And then as you grow your community, there's also the aspect of nurturing it and building it. And I will mention a little bit more about this later. But once the community starts growing, there's the aspect of a code of conduct, which defines for your new members how they engage with your community, how they should behave themselves, what kind of values they should hold, but also what kind of values they should expect. So if there's any kind of conflict in your community, the code of conduct should also address how these things will be handled. Then in terms of facilitating open and collaborative work, this would be the next point. As we mentioned, all of this would be very hard to do without a versioning system or without doing this in the open. So a versioning system, these days, one of the most popular is Git. If you have been working with software for a few years, you might have seen Mercurial, you might have seen Bavar, you might have seen other things like CVS, SVN, and so on. All of these, they have always the same idea, which is to track changes, to keep track of all the modifications that the code goes through. But for instance, what made Git so popular nowadays is some of its features that allow very easily to contribute, to work offline even, to do quick prototypes by using a feature called branches, and to also have all the history along with you. And here I would like to also emphasize the value of having the entire history of your project with you, because although it may seem a little bit like unnecessary, so to say, you have all the software that the latest version would be what you would care about, or at least what your users will care about. But you may be surprised how often it happens that there's a certain change that is introduced, a bug appears, and then the answer or the easiest way to find what actually happened is by looking back in history and figuring out when did this behavior change. Then at a later stage, you may want to do the first release, as we mentioned before. And here I would like to highlight a bit of a standard called semantic versioning. So the way it kind of defines is that for every, so you have a series of digits or numbers separated by dots, and optionally a label at the end, and this defines your version. And additionally, there for each of the digits, there's a set of rules, so to say, that apply. So if you have, for instance, a small bug fix that didn't really change much in terms of behavior of the software, but addressed one particular use case, this could be an increment at the level of a patch digit. But if for instance, you do a very large rewrite of the software and a lot of the internals changed, and anyone that might be using it as a library, for instance, will need to adapt, then this would be a major change. So you'll be changing the first digit of this. Now, in addition to the value of the history that I mentioned before, we also have changelogs. So changelog, much like the history of the Git or the repository itself, is a bit of a human readable or a digested version of the history of your latest changes between versions. And this is useful both for developers and for your users to understand what kind of changes happen from one version to the other. And if they, for instance, are still using an older version, if there's anything that they might need to do or to adapt to move to a newer version. So sometimes simply upgrading is not an easy answer, and having a changelog really helps to identify what were the changes. Then we mentioned citations as well. Brice mentioned Zenodo. Once you get to the stage where you have the first version released, having the version released on Zenodo already gives you a DOI. But if you are considering the full pipeline of development, you may only have a publication at stage 5, at the publication stage. And here the important point is that you not just tell your users how to cite your tool in order to get that recognition, but you yourself citing other tools if you are using them, because it goes both ways. And then finally, there's also, although what we are discussing here is just general practices, there's new, more recent movements such as making software fair, which stands for findable, accessible, interoperable, and reusable, which is another way to look at improving the overall quality of software and making sure that these projects are sustainable over time and accessible. Then on top of this, I would like to highlight documentation. So documentation comes in many forms, and it's for everyone. It's not just for users, it's for contributors and for collaborators. A very typical initial documentation is a README in the repository, and this is perhaps the simplest form of documentation, where you find a very short description about your tool, what it does, what its purpose, perhaps a short demo or a mini tutorial of how to use it and to quickly get started. But it can cover much more. It can include author lists, citations. It can include pretty much a summary of everything that is relevant for the project, including links to more extensive documentation. Then on top of this, I would like to highlight 2 types of documentation that are very common. The first type that is more directed towards contributors or people that handle the code directly, and this is comments in the code itself. It can also be doc strings, which some of them may be accessible to users, for instance, if you're developing a library. And these are often language specific. So these may be things that there's specific syntax of how to do it in your ecosystem or your language. But this is at the level of interacting with the code. And then on the side, you also have the more extensive documentation, which can include tutorials, can include examples, detailed explanations, and more verbose forms of detailing what is actually happening or how to use your software and your tool. And I'm highlighting here some of the tools that are very popular these days. I'm a big fan of Read the Docs myself. And moving to the next step, I would like to highlight also in the case of doc strings, there's also something called doc tests, which you can see in this box here. And this is what brings us to the next topic. So testing. So testing is what I consider a triple value feature of software development, because it provides a safety net. So if anything breaks in your software, you can usually capture it with a test. And this ensures that if something breaks again in the future, you will catch it before it goes out or before it gets released. So this is a safety net for you as a developer or for anyone as a developer. Then tests themselves, they also work as a documentation platform. So I've on various occasions, I have for projects that didn't have much documentation but had tests, I've often looked at tests as a way to understand how should I use the software, how should I call this library, what kind of arguments I should pass, and so on. So this can be useful in that sense as well. And it also reduces the entry barrier for any new contributor to your software. So if you have a very complex software and you want to contribute something to it, it can be daunting, it can be scary even to contribute something, because you're not really sure what it might affect. It might break something that you didn't consider. So having the tests there also works as a safety net for your users or for potential contributors in the future by giving them the reassurance that that things will work, and they can see the impact of their suggestions. Then in the topic of tests, there's many different kinds of tests. I don't want to go too deep into the detail or the distinction of them, just to highlight that they can be done at many different levels. They can be done at the level of the individual function that you have to make sure that the function behaves as expected, or different components working together, or even that the final product that you're building behaves well or correctly as a whole. And this would be the functional level, for instance. And you can also have tests specifically for graphical interfaces or for any kind of user interface that you would replicate the user interacting with it. And this would be done at an application level. And then finally, all of this is obviously very language dependent. So the recommendation here is use whichever tools are popular in your ecosystem in whichever language you're using. If you're using Python, PyTest is, for instance, one very popular. You have also Hypothesis, which is another way of testing things. And if you were using Ruby, you could also be using Cucumber, which is a slightly different way of testing called behavior-driven development. But it ultimately boils down to you defining with human language what you want your tools to do, and then you actually test if that behavior stays or not. Then all of this, as you can imagine, as it grows in complexity, becomes challenging to do by hand. So as much as possible, automate things. And this is where a lot of the more recent developments in platforms such as GitHub, GitLab, and so on enable all of this. So you have what is called a CI and CD pipeline. So CI stands for continuous integration, CD for continuous deployment. And these are simply automations that allow you to run your tests at every change in your code. For instance, every time that something changes, you can tests will automatically run, and if something fails, you immediately know. So you know when the problem was introduced, and you have a smaller set of changes to look at to understand what might have happened. Coupled to this, we can also have a lot of really nice tools that help us ensure that our code is easily manageable. So Brice mentioned Black, for instance, before, which was an inspiration for a snake format. Black is a code formatter for Python. I would also like to highlight here the pre-commit framework, which contains a huge collection of plugins that you can enable for your repository, and you can use them either through a CI or even directly on your computer before or as you commit changes. And all of this is nowadays enabled in large part by free resources that are often given by companies and by institutes to support open source. And here I put free in quotes because they are made available, but they are not entirely free. So there is the companies themselves are the ones supporting this effort, and this includes GitHub, includes GitLab as well. Particularly in the case of GitLab, there's also the possibility of having a local deployment, which is what we do, for instance, here at EMBL as part of the BioIT project. We have GitLab installation running locally with different runners. For different needs and different projects, including the ability to present pages and websites directly from the repositories. And then something that is most visible on GitHub is where you have a lot of services by companies or even by GitHub itself automated through bots. So things that do automatic detection of dependencies when something changed, you automatically get notified. And there's even entire pipelines built automatically using these bots where they create the pull request for you. They may run the tests for you, and if everything passes, it gets merged automatically. And the entire process can be automated. Obviously, this would be something that you would do at a much later stage, such as in production. Now, all of this would not really be relevant if we don't mind the reproducibility. So we should be mindful of reproducibility. And here I would like to emphasize, excuse me, I would like to emphasize one aspect, which is that of packaging. So packaging is the ability to take your software and make it available to users. You may often see this as a topic that is considered solved or is not really relevant in a lot of ways, but it's actually a huge effort, and it's not at all an easy task. And that's why projects such as Bioconda became so popular and are so popular nowadays, is because they package loads of different software for bioinformatics, and they make it available to multiple platforms, including Windows, Mac, and Linux. And so the importance here is to make sure that your tool is easy to install to your users, and that the installation itself is somehow contained, or like the dependencies are captured in all of this. On top of this, we also have repositories, and registries. You may know PyPy, you may know CRAN, you may know Bioconductor if you're working with Python and R, but there's many others, like JavaScript has an NPM or its own repositories, and many other languages have their own registries. And here I would like to highlight this awesome compilation of registries that you will be able to navigate afterwards once the slides are shared. And then on top of this, because this problem is so complex, and often even through efforts such as Bioconda is not easy to actually manage all of this, there's also containers such as Singularity, which is a friendly solution for high performance computing, and Docker, which is more used in the wild. And these capture not just your software, but the entire collection of dependencies that you may have. As you imagine, all of this is very challenging to do by hand. So once again, automation is very important, particularly if you're going multi-platform. If you have a tool that is meant to be installed on perhaps Linux. Linux is not a single platform. There's many flavors of it. There's Debian, there's Ubuntu, and all of them have some variations and different ways to install things. So you may need to test all of this. And so automation is how you should go forward to kind of address all of these aspects. I would like to also highlight the philosophy that improper packaging is a bug. So if you get a combination of dependencies that is not really aligned, this is going to create a problem for reproducibility. So you should consider this, or you should see this as a bug. And if you want to dive deeper into reproducibility, I would also like to highlight the Turing Way project, which has an excellent guide on how to do reproducible research. Now, the next step would be to assess the sustainability of your project. So often in the past, there was this in a way, the academic word or academic software was often a synonym of poor quality. Luckily, this trend is no longer true and is not holding in great merit to a lot of these measures that we are presenting here today, and efforts such as FAIR, which addresses many of the problems underneath. And on top of this, there's also now a recognition of many career paths that didn't exist in the past, in part because there's now a lot more data, and it's becoming accepted that you cannot really address or handle all of this data if you don't have methods and software to help analyzing it. And so you have positions such as research software engineers, you have data scientists, data analysts, cloud engineers to kind of cover the breadth of both infrastructure and different technologies and different aspects of research nowadays, both from the engineering aspect and the data management or the data analysis aspect. And in all of this, and very similar to the effort that we did with Elixir Europe and the software management plan, there's the Software Sustainability Institute in the UK, which assembled a sustainability evaluation checklist that you can follow, which precisely tells you what additional things you might want to do in your project, much along the lines of what I've been presenting here today, that will help you make your project more sustainable. Then last but not least, the aspect of community. Brice already mentioned how important it is. So community is something that we should build. It does require quite a bit of work, but it's something that we should build and we should cherish. We should reward all kinds of action. You may find users that don't really code, but they are excellent at writing documentation. and vice versa. You may find that some users or some people just like to navigate through issues and kind of organize things. So really reward all kinds of interaction with your projects, because this will be super helpful. Empower active members, so anyone that is already engaged with the project and is clearly outstanding in your community, make sure to empower them and give them the ability to do more. And something that I find particularly useful to relate to a project is to define personas. So personas is a little bit of a profile that can be inspired in members of your community, or it can be simply a fictitious character, but that defines one type of interaction that you would like to have in your project. And then, as you may wonder, as you may think, all of this would not be possible if there's no opportunities to engage. And this can be through, for instance, labeling issues as a good starting task for a newcomer, or it can be through activities like hackathons and so on. Sorry. Pardon me. I'm a little bit over time, but I'm almost done. So this to better the world and to do it one merge request at a time, to end in a bit of a cheerful tone. So in summary, accessibility, we want to have the code versioned, we want to have it well-defined and a well-defined engagement process. Documentation in code and elsewhere, very important for pretty much everyone involved with your project. Testing automation for all of its benefits. The community and sustainability will keep your project alive. Often you may move away from it, but your project will continue alive because your community keeps it alive. And to finish, just a few of the resources that Brice mentioned already, such as the Chan Zuckerberg initiative, and also a few others, both in terms of funding support, as well as other initiatives to help you guide your project through sustainability and to make your project more successful in the future. And with that, Alex, I will give the floor back to you.
Yeah, great. Thank you very much to both of you speaking. I would like to say, so please add any questions you have to the question and answer box so that we can have a discussion later. I would very quickly like to say all our webinars or there will be more webinars upcoming about open access and open science, and you can find them on our EBI training webpage. And we also record all of our webinars, and you will also find, can access the recordings through our EBI training webpage. And the relevant links will also be provided with the slides. And don't forget, please, to answer or respond to the feedback survey at the very end of the webinar, because this is very important for us to develop future webinars. So I see there is a question in the question and answer box. It is a bit longer, so maybe you look at it as well, but I will read it out as well. So, and then he asks, hi, I'm part of a rare disease patient group, and we ramped up multi-omics pipelines using a lot of public databases like Ensemble. During the development, a lot of smaller Java OS projects have been implemented, and then he gives an example on GitHub. You mentioned that some OS projects get fundings. Can you elaborate who is applicable and how to apply?
So I can perhaps take that one. So for some of the funding agencies that I mentioned here, this is not uniform. So every kind of funding opportunity has its own requirements. So this would need to be assessed on a case by case. But for instance, there are some initiatives that reward originality. So if your project is very unique and nothing like it exists out there, then this can be a strong reason to apply to those. But for instance, the Chan Zuckerberg initiative is quite the opposite. They reward projects that are well established and have reached a high level of maturity, but actually need funding to continue development and to improve perhaps some aspects and to continue alive, because sometimes funding is the limiting factor. And Brice, I don't know if you want to add something there.
Yeah, no, I mean, there's a nice list of the selection criteria and eligibility as well on their website. But yeah, it's as you say, Renato, it's more established, but it is all about like maybe how big your user community is, how actively developed your project is, how quickly you maybe go from an issue to solving it, how easy it is to contribute. You know, there's a whole list of stuff. And it all has to do with, I guess, that maybe how useful your project is, and how big of a community would benefit from the funding.
Okay, thank you. I hope that helped, Danny. There is another question from Henry. Thanks for the nice overview. Could you please point out once more what the difference between GitHub and GitLab is at EMBL?
Yeah, so it's a tricky question, because it kind of goes in a different direction. So GitHub and GitLab, they are both commercial platforms. They are companies, so to say. Exactly what is the role of EMBL in all of this? So GitHub is a platform on its own and exists only on the github.com address. GitLab also exists as a gitlab.com platform, but they have a product which is open source itself that you can install locally. And this is what we have running in EMBL Heidelberg as part of the BioIT project. And this means that we can run it internally. We can have our own set of rules or create criteria for how to make things accessible. And so you, for instance, if you have some data privacy concerns, then you can have this confirmation that the data stays within EMBL, and only if you want to make that data public, then it will go outside. So both modes exist, and yeah, and ultimately this is all enabled because the GitLab platform can be installed locally.
Okay, thank you. So Andre added another question, and maybe I did not catch it. If code is deposited at GitLab at EMBL, does it considered copyrighted and belongs to EMBL, being open source? To whom belongs the rights by default?
Yeah, so that's a tricky question as well. So this is something that I'm not sure I'm in a position to answer. This might be something you should direct to the legal office at EMBL. But what I can say from discussions in other sessions as well is that it's more complicated than simply who is actually kind of owning the data, so to say. If you have a contract with EMBL, there's obligations in that contract, and this also means intellectual property. And so it may not be entirely clear how this is handled. EMBL is supportive of open source, but for instance, if that open source project is being commercialized by other entities, then this creates a bit of a difficult situation and would need to be assessed case by case.
Okay, thank you. So Stephen has an interesting comment. Thank you both for a good overview. While this is not necessarily a question, I do appreciate including the code of conduct for users and contributors. In fact, I would emphasize that first in the project's community engagement before allowing downloading and coding. So I think apart from this was everything. So I would like to thank both of the speakers again for being here today. I hope that all attendees take something home, and also the importance about making the code open, and are motivated to contribute to the open source software community. I thank you all for being here, and yeah, see you hopefully for next week for the next webinar we have in our webinar series. Thank you and bye.